So I'm Clive Cartwright and I'm a GIS analyst based at the British Geological Survey. And I was technical lead on this particular project, along with actually Henry Holbrook himself as well. So hello, Henry. So in terms of the running order, I shall give a brief introductory overview of what scour is and why it is important that we try to address the growing needs to mitigate such events. And then I'll introduce GeoScour dataset package briefly, before homing in on the dataset that we want to concentrate on, and that is river lateral flow. So I'll start by giving a brief overview of what is river scour and why it is important. So river scouring is a removal of sediment or engineered materials from the bed or banks of a watercourse. It occurs when the forces imposed by the flow on a sediment particle exceeds the stabilizing forces. River scour can occur gradually or periodically during floods, and this depends on the characteristics of the sediments, the riverbed, and the capacity of the river to transport those sediments. River scouring may occur due to high flows or due to a change in the riverbed slope, causing extreme localized hydraulic forces. Bridges in Britain are often historic structures that span centuries, and as a result are constructed in a wide range of materials. Many bridges and viaducts also carry key infrastructure such as utilities and communications. River scouring is an important threat to these bridges, as well as to river structures such as flood defences and electricity towers, or pylons as we call them. Recent years have witnessed major storm events causing a significant rise in river stages and increased river flow velocities. So Storm Desmond in December 2015, for example, caused huge damage to bridges across Cumbria, with a repair bill of around £4 million. The National Park suffered damage to 257 of its bridges. After Storm Frank hit on our shores, also the same month, same year, £3 million was approved for remediation of damage in Scotland. So that was just 2 storms in 1 month. Scour-related damage and failure results in costly repair and isolation of communities. So according to predicted future weather scenarios, the extreme weather events similar to those recently observed are set to increase. The Climate Change Committee's recent independent assessment of the UK climate risk has highlighted that the risk to bridges and pipelines from future erosion requires further investigation. Here's a good example of scour activity along the River Greta. It's just outside Keswick, showing the scouring side of the river eating into bedrock. The debris from scouring upstream can be seen deposited on the left-hand side. This event again took place during Storm Desmond in December 2015. If you look, note the layer of surviving topsoil and the trees above that scour line. This clearly indicates the scour hasn't affected this side for some decades. But on the event of an extreme heavy storm, the bedrock gave way to the high velocity of the water. But what is not so clear in this photo is that along the top, behind that bank of trees, lies the A66. So generally, scour is analysed by hydrologists and hydraulic modellers for specific case studies, and usually at a site scale. These focus on erosion and scour to construction and protective materials. The inclusion of detailed rock and sediment properties is often overlooked. In addition, there are limited fluvial scour models that provide a national overview of the scouring hazard, and even fewer that include a landscape evolution from a geoevolution perspective. This gap neglects important factors that could improve understanding and modelling of our scour risk in riparian environments and reduce existing estimation rates of scour potential in current model outputs. Based on these observations and that the frequency of extreme weather events resulting in significant damage to infrastructure due to scour and flooding, BGS Scour version 1 was released in 2019, providing a combined geological and geomorphology assessment tool using site-specific case studies to build on a national scale model. GeoScour, here we go. So BGS GeoScour 2, the second version, was only released a couple of weeks ago. So version 2 is designed to provide updated, detailed riverine information for assessing the propensity for river scour at any given reach of a river across the whole of Great Britain. This national coverage is demonstrated here on the left of the slide. It is intended for use as an input to hydraulic and sediment transport models, as well as integration into screening or planning tools. These can provide hotspots of potential risk areas to aid in the prioritisation of remedial action, or help define river infrastructure that's most at risk. This can be achieved at a catchment scales, as shown here in the middle, and at riverine scale, as you can see on the right. The tier 3, which is the group of data sets that we're looking at now, is all riverine data, and it can be utilised to assess the geological susceptibility of bridge infrastructure, indicated here by blue dots across the whole of the catchment, as well as honing in on the riverine level on the right. The latest release consists of 9 datasets at riverine level, all to be used at no more than 1 to 50,000 scale. They include updates to the riverine geological properties, riverine morphology, and surface geology susceptibility layers, with the addition of new data layers providing information on bedrock geology susceptibility and river lateral erosion. The river lateral, oh, that's a mouthful. The river lateral erosion dataset is the one we're going to look at now, because this is the feature that requires a mapping method that helps to identify the scouring side of the river as you travel downstream. So during 2019, the 2 stakeholder workshops were held at the BGS, with a focus on testing the usability of the recent release of the first release of GeoScour. Feedback from these stakeholders highlighted a need for the identification of the erosive side of the watercourse, and this to help asset owners, planners and developers understand more accurately what's going on. As you can see from the diagram on the slide, the scouring bank is on the outside of the river bend, and where this changes from a hard, resistant lithology, the dark grey band, to a softer one, the yellow band, the stability of the scour bank is reduced and susceptibility to lateral scour increases. The interpretation of the geology and its susceptibility to scour is assessed over set distances using transects perpendicular to the river line. And the assessment is based on the worst case geological susceptibility data and considers transects up to 200 metres from the river line. So based on this understanding, we embarked on a creation of a new river lateral erosion dataset, which provides an assessment of any lateral change in susceptibility to scour, which is also calculated on the scouring bank of the river course in the direction of flow. So I ran away, and my first thought was to look at the DTM slope model and see if it could identify any physical evidence of river scour in the form of steep river banks. This involved simply classifying the slope angle on a 10-metre DTM slope model into 3 classes, low, medium and high, purely based on angle. The results were then attributed to a polyline river dataset via GIS spatial interception. So there's the results. The results, not very useful. Firstly, the two source datasets often varied in spatial proximity. And due to possible differences in cartographic capture, scale, and accuracy of the DTM, null values for large parts of the polyline would appear. Secondly, most river datasets, when you look further inland, become single line features and therefore make it difficult to visualize riverbanks that are prone to the effects of scour, especially with a lack of compatibility between the scales of the datasets used. The final dataset output, well, it also needs to be the same as a baseline river dataset we used for the original GeoScour dataset package. So thirdly, a steep angle of slope doesn't necessarily reflect the most susceptible points of scouring. Assets such as bridges and buildings would be equally potentially susceptible to broader, flatter valley environments that simply do not show via this method. See on the right-hand side of the image, there's clear evidence of meandering that's completely overlooked. So a new approach was needed. So back to the criteria. First, use the open rivers dataset. So in this case, a watercourse linked dataset. This is an open source dataset that will be used by many stakeholders. Using open rivers potentially enables stakeholders to seamlessly slot this potential dataset into existing models. Also, the OS Open Rivers dataset was used in the original version of GeoScour, so continuity was important. Secondly, identify and only provide geological susceptibility of the scouring side. This was a key request that emerged from that stakeholder workshop. And deliver the results in a form that doesn't or do not mislead the user or give any grounds for potential visual bias. This is a cartographic issue, so as not to deliver the results in such a way that they would be considered absolute. For example, the visual representation of spatial boundaries and extents, and the terms used within the attributes, i.e. appropriate wording. So initially, applying a progressive buffer based on a Strahler river order to an OS Open River dataset was considered a good place to start. And the idea being that a weighted coverage or extent of scour susceptibility by proportional river size would be a useful proxy for water velocity or capacity. The image here demonstrates the application of progressive buffer coverage extent geologically susceptible areas based on that scouring side of watercourse by river order. Albeit addressing the key requirements of stakeholders, as you can see, this example has visualization issues. The buffered blocks of geology imply an absolute boundary. This can be interpreted by the user as definitive. For example, if you have an asset that appears to be on a polygon boundary, it often causes confusion, i.e., is it vulnerable or is it not? So that's not a good start. And the gaps on the non-scouring side are also confusing. You've got all these holes everywhere. In fact, without the visual cue of the river line, it's difficult to know what you're looking at and what you're supposed to be looking at. And then thirdly, the buffered geology is also governed by the river order value. Restricting the lateral data by river order is a crude way of measuring water velocity and capacity. So we decided to drop the river order idea and purely focus on the geology, which after all is our area. So final methodology became write a script to identify the inflection zones along the OS Open Rivers polyline, identify the geological susceptibility of the scouring side of the watercourse at regular points by recording multiple readings using transects perpendicular to the river line, and deliver evenly spaced point data along an entire river course in the direction of flow, all of them fully attributed with scour susceptibility assessed at distances from 5 to 200 meters from that river line. So in the end, this was achieved by removing lakes and inland bodies of water from the OS watercourse link data set. The coastal regions were tidied up using OS boundary line, high water polyline feature layer as a clipping mask, if you like, and this prevented null data points appearing in the end product. I've got an image here of just a close-up of part of that river network. The river polyline is then split into segments by its vertices. Once all the river lines are split into individual segments, a long integer attribute field is then created and labeled. I called it angle. And the angle field is then populated by the bearing in degrees for each consecutive line segment as you go along the course of the river. The value for the bearing is then compared to the previous vertex or the line segment. For example, if the river line changes direction, the difference in degrees is noted. You then have to make all the negative angles positive and override the issues of the coterminal angle, the naught, or is it 360, in order to identify the difference in angle change based on the previous vertex. So we're traveling down the line and working out the angle of difference. The positive result will be used to identify scour bank left, and the negative will be scour bank right. And if there's any straight lines, which is you do get, those zeros will be classed as neutral. We're now halfway there. So note how the join between the blue and red segments failed to identify the bend of the river. So where you've got loads of blues, you can see it's scouring to the right. and whereas loads of reds are going to the left. But where the blue and the red join together, we don't know what's going on there. So to overcome that bit then. So before we do this, we need to make a feature of all the nodes from the line segments that touch two segments only. So I'm ignoring the confluences and the start nodes, as seen here in yellow. These new points will adopt the downstream segment attributes that will be required later. We can now split all the river segments in half by using a segment centroid feature there. And here's a close-up. So once split, we can now add the inflection attribute required to split segments using the original node data created earlier. So there we go. You've got the centroids in the middle of the lines, and I'm going to cut them in half. And now I can apply using these nodes with the information from earlier to supplement the new lines. So there we go. So now we have no joint that's ambiguous. They are now assigned what they should be. So we've got a proper left and right bank river data set up. So next thing is a transect. So a Python script is run to create a point shape file to show lateral susceptibility. So this generates points every 50 meters down the river and processes each point to determine its attributes. The inflection of the river at each of these points is used to determine the direction to extract the worst geological susceptibility score at varying distances perpendicular from the river. So this is done by calculating the bearing of the river at the point, retrieving the perpendicular direction, plus or minus 90 degrees, depending on it, if it's a left or a right inflection, and then calculating the XY coordinates for 5, 10, 20, 25, 50, and 200 meters distance from the river point. The final result is a less cluttered view that allows a user to interrogate the desired point of interest with relative ease. And there's no visual cue penning you into thinking that your asset is in or out of the zone of potential influence. You will simply know if your asset is within 200 meters of the river line. And if the result is low susceptibility, you may be safe to concentrate resources elsewhere. And here's a spot marked in red, indicating the location of that photo I showed earlier. River Greta near the A66, actually the A66 is a little bit further away than it looked on the photo. So just outside of Keswick. The dataset here shows the geology susceptibility to be medium to high. And here's that photo again. So it is an issue to look at. And that's it. I'll leave it there. I think I rattled through that fairly quickly.
Thanks, Clive. That was excellent. We're now opening up for questions. If you have any questions, put them in the chat. I was just wondering, Clive, does human activity affect scouring in a meaningful way? Is that something that needs to be considered?
Yes. Well, yeah, in a positive way. Well, actually both ways, of course. If you've got channeling where you've got straight rivers or straight water courses, you can get scour on either side because it gets kind of almost like a Bernoulli effect going on. So it depends on the materials used to help contain those channels. But yes, eddy bridges will create eddies that will help scour to take place. Yeah, so the humans do play a role in that. But of course, then there's flood defences. So yes, we can actively mitigate the damage as well.
Great, thanks. And we have Kirsty saying, thanks, Clive, a really interesting presentation. Anyone else have any questions before we move on? Is this something that is quite typical that the British Geological Survey looks at? Erosion and that kind of thing? Is that a large part of the mapping at the British?
Yes, very much so. I mean, this is just the rivers where I've got rid of the slideshow. Can you see me now? Yep. I'm back. Good. Yeah, I wasn't sure for a second. That's fine. Yeah, certainly erosion. We're doing coastal erosion as well. That's a data set we just released. So That is slightly more complex because of the coastline can be not just one or two geological strata, it can be up to 7. So it gets very complicated. And yes, and an awful lot of the rivers are made up of alluvium, but that alluvium is built up from debris collected from the geology further upstream, which has varying levels of durability to water scour. And of course, as geologists, we can actually grade that as well. So they're the two big ones that have only just been released, yes.
And we've got a question from Claire. Will the process that you advised be used for other uses or identification?
Well, as in, can this be used with other data sets? I wonder. I mean, if that is the case, yes, we've deliberately tried to design it in a way where using OS open source river data, we know that some of the stakeholders also use that information. So this should slot seamlessly with existing models. So yeah, we've worked hard to try and make it usable, quite compatible is the word I should say. Is that answering that one?
Yeah, so you're saying it can be applied to other issues?
Yes,
yeah.
Yes.
Okay.
Absolutely. I mean, yes, any land management and any developers and planners would be worth considering this. But one of the main focuses was those asset owners who own old bridges, especially, that have been there for a long while but are now vulnerable. Where should they allocate their resources? They've got hundreds and hundreds, if not thousands. It depends who's in control. Where do they, they haven't got a bottomless pit of money. So they need to target the right areas. And this is what this data helps do.
All right. And one from Jim. How often do you review the data?
Right. There's many, right, the inputs, we will be reviewing it fairly frequently because the OS will update their riverine data set. And if other people are using that, and we need to have this fit in with that, that's one of the main criteria or issues we have to deal with. But also our geology, our knowledge, our database will also be updated. And at a certain point, that will also feed into this for a new version.
All right. Thanks very much, Clive. That was excellent.
Okay.